So my name is Kai, and today I'd like to spend the next 30 minutes to talk about an internal framework called Delphi. And we use this framework to essentially forecast a global global marketplace. And our way to get there is essentially to utilize a hybrid approach. What I actually mean with all these three things I just said, I'd like to explain in the next 30 minutes. So about 5 or 6 years ago, we thought about how to do forecasting in a global marketplace. And the fundamental challenge we saw is that machine learning is actually really good at interpolation. Because the universal approximation theorem states that essentially if you have a neural network with an arbitrary number of hidden layers, you can approximate and interpolate any given function. So how does that then look, though, when you're trying to project it out in the future? And really see a fundamental disconnect between interpolation and extrapolation. Because the problem always going to come down to having on your training set, having really almost no error, but then you predict it out into the future, there's always going to be uncertain things happening in the future. So then we spent some time, and the main author of this is a physicist, and he always had the strong ambition coming from physics that there are those theoretical physicists out there who essentially predict the world from a lab using a theoretical framework to explain the world. And we really thought how we can connect those two things. And I mean, just to jump on last week, what happened here to just leverage that excitement is that people were able to predict how a black hole would look like only using theory, and to have that exciting connection to predict things outside of your data using a robust theoretical framework. This is what we see as the foundation of Delphi. Yes, so this is then again, if you try to connect interpolation and a strong theoretical framework to then have better predictions in the future. So this chart, I'll just try to illustrate how we do have a theoretical framework that we're trying to understand the business in, but we combine it with statistical estimation methods to essentially predict rates and occurrences of certain events. So we really think that this is a really strong combination and a hybrid approach between those two things to reliably predict the global marketplace. So what I'd like to spend, after I've given you essentially like a TLDR version of what I'm going to talk about in the next minutes, is to talk about the statistical forecasting aspect. How do you estimate the seasonality of demand and supply? How do you then also come up with the underlying metric graph? And then how does Delphi actually give you a singular API to realize both of those aspects? So, how does Delphi realize this hybrid approach? So when we now think about statistical forecasting, there are many models out there that actually allows you to predict time series data. I mean, everybody knows about ARIMA, LSTM seems to be fashionable nowadays, but we always really want to have interpretable models. Because at the end of the day, the only way to have it tie back into your causal metric graph is just to have interpretable models. What you also want to gain from forecasting is to derive business insights from having the structure model behind it. Because if you have a prediction and trying to explain to executives why you get to the forecast for this region, they're always going to ask why, how did you get there, and what were the immediate steps that they might find something to essentially leverage for product changes. So that's why we're always going to prefer interpretable models over black box models. One of the most dominant interpretable model throughout history, throughout statistics, is the generalized linear model, which is a very simple model that allows you to model a link function, and then you can have an exponential family that you have your link in, and then you essentially have still a linear model that you can interpret the individual coefficients. However, GLM is neat, it's simple, but it really lacks two fundamental things that we then found extensions for. One of these extensions is the generalized additive model, which essentially extends the generalized linear model plus something that gets a seasonality. I mean, predictions in the global marketplace are highly driven by seasonality. What I mean by this is you do have different effects for weeks and years and days of the week. And generalized additive models extends GLM with this concept. I'm going to talk more about this in the next slide. What we also have is essentially unexpected events. So things that we don't account for, but we actually see in the data already observed. And they use something called the generalized linear mixed effect model that allows you to elevate your estimation for the future days, given the existing information. I'm going to talk about that more in the next few slides. So this is the generalized additive model. What I want to get across here is, first of all, what you're interested in modeling is this link function of your expected value for your response And you can model it as the sum of smooth unknown functions. What I mean by this is instead of just having a linear coefficient, what you're also interested in expressing this covariate through a basis function. And what this allows you is essentially have a lot more flexibility that allows you to get to seasonal trends that are cyclical, for example, or cubic. So you essentially get a lot more degrees of freedom, but it still fits in the framework of GLM. So you remain this interpretability. As a fair disclaimer, I stole this wonderful chart from a statistics post on this because I think they've done a great work with GAMS and they have a great post about that. So what we do is we represent then our seasonality as smoothing functions using something called a B-spline, which is basis spline. There's a wonderful R package out there called MGCV that essentially realizes this and allows you to scale up to a lot of data. And yeah, if you ever want to use generalized additive models in R, I highly recommend MGCV. It's a tremendous package. So now I'm giving you some theoretical understanding, but it's probably best if I walk you through an exact model that we do. I'm going to walk you through the theoretical underpinnings of it, and then also how do we then glue this in code. So Airbnb, what we're mainly interested in is figuring out how many bookings or nights booked we are expecting. So what we utilize to get to an estimate of the number of nights booked in the future is that we decompose each booking into different dimensions. What I mean by this is every booking we have on the platform, and apologies for European date formats, I realized it's too late, but you have someone booking from the 20th of March, booking in the future, and if you decompose this booking into 3 dates, because the person is staying 3 dates, you can represent this as a matrix like this. So essentially you have someone going from the 20th of March to the 25th of March, and he stays 1 night. So this is only one booking. You can only have a 1 in this entry. And this is how you can decompose a single booking. What you're also interested in, what also tends to be highly informative, is just the distance between those things. Because people have the tendency to do things short term, and therefore you tend to have a lot more bookings popping up right before the date. So we're trying to estimate this effect as well by using just the difference between those two things. But then if you just have this demand-driven approach on estimating number of nights booked, you're clearly missing something related to supply. And this is how we capture it. We use something called the Occupancy Index. It essentially tells you how much available good supply is still free for these individual dates. Essentially, you add another column to your model matrix that tells you how much of the good supply, and good is a tricky concept here, I'm aware of this, but how much of the good supply is left in those markets. And you then end up with a matrix that tells you how many nights booked you're going to have from where going to when, and how much of the available good supply is already used up. The next question is then, how do you then stitch all this together into a GAM? So given that I just talked about GAMs, I'd like to make this connection because I think it's a very illustrative example. So in here, and people who are not too familiar with GLM, just bear with me. I hope you get the bare bones of this argument. But essentially, you're trying to model a value, which is the number of nights booked, which should be Poisson process since you count the occurrences of something happening. What you then are interested in is essentially different encodings of the day you book from. So if you think about the 20th of March, this will happen on a weekday, and then essentially how many days have passed since Airbnb's inception. So you account for the growth based on a booking date. And then there's several ways you can encode this year-over-year growth. What you're also interested in just known events, because right now you know essentially when Easter is going to happen and when New Year's are going to happen, and you're trying to account for that, but just encoding this. But now comes the smooth unknown function that I mentioned, and why we really like GAMs. So GAMs have this wonderful property that you can just represent this covariate, which is share of the year, which is just a way to encode this. And think about just encode it between 0 and 1 every day of the year, ignoring leap year. Essentially, you get this then to represent a function using a basis. And this basis can have several properties. One of these properties that we like is having a cyclical function that because there's a relation between the first and the last day of the year, as well as also having a cubic function because it gives you enough degrees of freedom to estimate the shape of our seasonality. And as I mentioned, you also have delta, which is the difference between the booking date and the night this booking actually happens on. We also estimate this by individual week dates, because this is a highly informative predictor. It's giving essentially what day you booked to, what weekday is this. You then have the same analog on the date this night happens on, and you do estimate the share of year in this, as well as the weekday, and you also have events that happen there, and you have a growth term. What you do in the last column of this matrix, you take into account the occupancy index. Essentially, how much of the goods supply for those specific dates is already used up. And you treat this as an offset for technical reasons about GLMs, but let's not go into that much detail here. But this essentially tells you how we get to seasonality. What we then also have is something called the mixed effect model. Mixed effect model essentially extends this bare bones of the most boring linear model you've ever seen, but it extends it with another parameter that you can treat as a latent variable model that allows you to essentially estimate variance for each individual data point. So you don't assume constant variance. You allow for much more flexibility. And we can do this because we have several observations for future dates. Because I've just given you these combinations. So you observe the night's books that happen for the 24th of March from all the previous days. And you can look at the variance between those observations. And the reason why we use this is essentially to leverage the number of pre-existing bookings. So if you see at this plot, you see 3 colors, and apologies for not making this bigger for people in the back, but you do already have a number of existing bookings. And you can see that this blimp here is just orders of magnitude more than the other data points around that. And then you can treat this as a latent variable that you do an estimate, a variance for each of these observations, and then you do the prediction on this. And if you look at the red color here, you see that if you do not treat this as a random effect and draw one random effect for each of these dates in the future, you just pop up the forecast for that date slightly. But if you use a random effect, you can see that this plays a much higher role. And if you then lay over actuals, which I can't do here, but you see that this works much better out than just using it without a random effect. So what I wanted to cover so far is essentially how we use statistical models to estimate supply and demand, that we're using generalized additive model as well as the mixed effect model to estimate the seasonality and undetected events on supply and demand, and how this interaction works then using the occupancy index. What now comes is essentially why we consider ourselves a hybrid approach. We are not only interested in getting the statistical shape or the seasonal shape of the year right, we also want to have a strong theoretical understanding of our business, because it allows us to make us more reliable predictions in the future, as well as it allows you to leverage insights from this model to drive then business insights and changes in a product. So this is Fermi. Probably everybody in this room has once in their life had to answer the questions, how many piano tuners are there in Chicago? If you generalize this problem, this was essentially introduced by this gentleman. And he really likes to understand things by breaking it down to smaller subproblems. And using this approach, using this framework, you can always come up with a causal model about the world. Because I still wholeheartedly believe that humans are better than machines at finding up the causal models. There's a debate in statistics, but right now I still think we should, as humans, come up with causal models about the world. And using the Fermi process, or treating it as a Fermi problem, is a really good approach to this. If we then try to do this with Airbnb, how many nights booked happening on a given date, you end up with some version of this. And this is not the answer, but this is a part of the answer. Essentially, you have nights booked as the outcome all the way at the end. But to get to this, you can take actually several paths along this metric graph. So what you can estimate, and as I just walked you through this model, is how to get the number of nights booked. But then the question is, how do you get to bookings? Well, you can just estimate something, a share model, which is then a binomial regression that estimates how many bookings happens per night booked on a given date by user type. And as you see, we do have the dimensionality aspect here, as we cut our users by past users, by new users, by past bookers. So you estimate most of these things in several dimensions and treat them individually. So therefore, you essentially try to realize this metric graph for different dimensions across time. And this is then essentially combining those two approaches. You end up with something that we refer to as Delphi. And yes, so what does Delphi then realize? Essentially, the cool thing about Delphi is that it provides a singular interface to express both components by just doing one call, essentially. So what you're doing is you specify the computational engine that allows you to express this metric graph, as well as the underlying statistical models by a single function. And I'm going to show some code later of this. But this is what we built Delphi for, because we didn't see anything out there that actually realized the same thing. So we decided to build one single computation, one single API that realizes all this. And what is essentially the output of this is an Airflow DAG. And so you can treat, the way we schedule all these statistical models is that we realize there's a big Airflow DAG that has data ingestion as well as statistical estimation part of this DAG. And then you end up with a DAG that has several thousand nodes, and then you can just schedule this in any company that has Airflow. And what's neat about this is that you can scale up your estimation of these models just depending on your Airflow cluster. So you can scale up your model, you just have to essentially increase the size of this queue in this Airflow instance. What is also getting produced by the single API is something we call the computational engine. Why do you need a computational engine here? Because at the end of the day, you have this very big metric graph, but you need to still stitch it all together. You have all these individual estimates, but you need a place where you stitch it all together. And one of the major benefits of this is you can do something called scenario building. I'm going to talk about that a little bit later, but I wanted to highlight is here. We built this first in Python, but then realized that it just doesn't have the speed that we actually needed to realize all these computations. So we ended using Python, which essentially is Python, but you have the ability to do low-level bindings to C, and then we exposed all those Python functions in Python. And what we then used is we created a GUI on top of this computational engine and on top of this Airflow graph, where you then have access to this metric graph to use something we refer to as scenario building. And everybody's ever worked with finance, there tend to be two very dominant questions, which is first of all, the forward-going look on your business, which is if tomorrow we would have 10 million more users on this website, how would the end of the year look like? And to avoid all those one-off Excel models and all of these scenario buildings, we essentially realized this as part of the GUI. So what you then can do is, I'm going to show this a little bit in the next slide, is that you can put your assumption about the future behavior of the business into this model, and it would leverage the metric graph you defined, as well as the statistical seasonalities you also estimated. So it's a really, really neat way of how do you combine those two things. Another aspect of scenario building is the backwards looking, which is essentially the goal scenarios. Executives really are interested in what would we need to do to get to a certain exit rate for a specific country. And we can realize this as also part of Delphi. And to realizing those two operations, there are several approaches to this. What we went with is essentially you treat this as a system of equations and use a very simple secant method to essentially find a solution to a system of equations. There are some, you could have more structure around that when you think about elasticity and things like this, but we currently do not do that. So right now, essentially, secant method to do backtracking to this, which is very similar to goal seeking. But yeah, this is what Delphi is. It uses those two aspects, gives you a single API, and then it can express your models. So how does this then look like? Again, this might be a little too small for people in the back, but what you're interested in is a metric. And this metric, as I previously talked about, is nights booked, or would be nights booked in this scenario, which is the number of nights booked that happen on individual dates going out in the future. So the date X, as I previously referred to, is the day you're staying at. But you're not only interested in this metric, we use something called a facet, which is essentially a metric on a single dimension. And we then specify on these individual dimensions, you have to also do the prediction on. And what you then also can do is, first of all, you need to have access to a data warehouse. So you have to implement based on your data infrastructure, a data warehouse operator that gets you this data. This is very akin to an OLAP cube, but we realize the thin layer on top of this, then you can get this data into the computational engine. What you then specify is, for example, that I talked about in order to predict the number of nights booked, you also need to know essentially how many listings you're going to have in this market. And you can also specify this as part of a facet on your nights booked. What you can also then do is to have this time shift occupancy model that I previously described from the GAM and the mixed effect model. And you say, I'm interested in this metric cut by these dimensions that you can pull from this data warehouse, and then run this model to produce a forecast with this. And this will generate you two things. One thing it will generate for you is an airflow DAG that allows you to run these models at a scale you're interested in, but it also builds a computational engine for you. And this is essentially, we refactored all of our code to make it that easy. It used to be much more complicated, but now we're in a place where this is much easier and it's much more readable. I wouldn't have had the confidence to show how it looked in the previous iteration, but now this is much cleaner. And again, we tried to make it simple, so then maybe even business analysts or people not familiar how Python, Python, and Airflow works can have access to doing statistical modeling and using computational engine. So this is kind of what we're trying to move towards to. So this is a very, very, very dumbed down version with no interesting data, because given we do financial forecasting, I cannot necessarily show you the interesting parts. But what I can show you is essentially an overview of this GUI. We are not a BI tool, but in order to do scenario building, you got to do a little bit of a BI tool. So what we ended up doing is to realize this GUI that is just a Flask app that runs on top of this computational engine. And you can, one back. And what you can do here is that you just tell, throughout those drop-downs, you can say what metric you're interested in, what dimensionality you're interested in, what scale you want to look on, what forecast you want to run this on, essentially. I didn't mention this, but we run this essentially monthly, because this takes a few days to compute all of this thing. But once you've run the forecast and you have generated the computational engine with all the necessary data, you then have the ability from this GUI to essentially tinker around with exit rates for individual metrics. Again, I had to hide all the interesting information here, but what you can still see is that, let's assume you're interested in bookings and you don't care about user type, you're just interested in a total number to the world, and then you can look at the exit rate by the end of this year and you will have the ability to play around with this. And just full disclosure, these are not indicative of our growth. I made up these charts, so they have no tie to the actual data. But this is essentially how we expose this to people who make then the adjustments. Because we have people who are tuned in the business that actually have an intimate understanding of what currently goes on in terms of product, in terms of policy changes, and no statistical model will ever capture this. Well, I would argue right now, no statistical model will capture those dynamics. That's why we always will need to have a human that still does this like last mile step, that takes an estimated seasonality, that takes something that gets you to events, but you gotta have a human at the end of the day to account for one-time changes and to account for scenario building that we then can use to communicate to executives. And yeah, I'm getting to the end of this, but before I finish, I would like to essentially highlight the man who wrote most of this, which is Marcus. He wrote most of this. This has been going on for several years now. We started doing this about 5 years ago, and there have been many iterations on this. And working on this requires a rather odd skill set, as we are spread between engineering and FP&A. So it's that Marcus is part of FP&A, and then we do have engineering resources who help us with the airflow scheduling, who help us essentially getting chef recipes right on the airflow worker nodes, as well as also maintaining the computational engine, and as well as having this Flask GUI on top of this, because it's what we're always iterating and always making the information more accessible in the GUI, because at the end of the day, you have to consume this through the GUI. So that's why we have engineering resources, as well as people who are closer to the business and sit in FP&A, and they are spending a lot of time of getting inputs from all the different business units to then essentially can make those human level adjustments to walk the last mile that otherwise we wouldn't do. And I know it's a shameless plug, but we're currently hiring for this team as well. So if anyone has any friends, feel free to reach out to me. I would also if you ever get interested in this, want to read more about GAMS, which I think is a super powerful modeling, Stitch Fix has a wonderful blog post about this. And there's always the classical literature, which is Simon Woods. And then you also have Gellman, who talks about Bayesian data analysis, which is probably the grandfather of mixed effect models. And with this, I'd like to conclude and open for questions.
Thanks. Just a quick question, particularly around the challenges working with the cross-functional team, especially with like FP&A that speaks a certain language and you know engineering that speaks another, and you know ML or data science that you know has this statistical background. Like what were some of the like how did you break through those barriers? And particularly interested in how you guys got to that the causal relationship that you showed.
So in terms of skill set, I think we were looking for very unique people, quite frankly. Actually, most people we have working here in finance have a background in statistics or mechanical engineering, which actually they're more akin towards understanding what we do. And quite frankly, it's a dialogue that needs to happen between engineering, data science, and finance, and just to develop a shared vocabulary. And that actually amounts to teaching people Poisson regression. And again, this is a lot of investment, but we had tremendous success using this approach. So it's teaching and people who are willing to learn. And in terms of coming up with this causal graph, which always seems to be the more controversial aspects of this, no causal graph will ever be perfect at capturing this thing. But essentially what we've developed, and it's a rinse and repeat process. You have one idea, then you do a forecast, and you clearly see you're missing one part here. And then you add something there. This is why we now refactored our entire computational engine to then have more flexibility of just adding something there. So it's an ongoing rinse and repeat process. We adding models, not super frequent, we're trying to do it more frequent, but I don't think we're ever going to be perfect. And it's actually, think about it this way, if you're missing something, there's also something interesting happening in product. So actually maybe you should pay attention, maybe something in product changed and you need to account for this now with a new model.